Hello, I am Chanyeok Jung from Dongguk University TTM Lab. The paper I will review today is Translate Patent Vacancies into Human-Readable Text, Identifying Technology Opportunities with Text Embedding Inversion. This is the bibliographic information of the paper. The paper was registered in the journal Advanced Engineering Informatics in 2025. The keyword and research objective are as follows. Table of contents encompassed like the table of contents in the paper. The introduction. In today's rapidly evolving technological landscape, the ability to leverage technological opportunities has become crucial for firm survival and growth. In this context, discovering new ideas through TOD plays a central role in securing competitive advantage. Among patent-based TOD methods, patent maps have emerged as a key analytical tool for forecasting promising future technologies. However, existing studies have faced limitations in clearly defining patent vacancies. To overcome these limitations, the GTM-based patent map generation method has been proposed. GTM projects high-dimensional data onto a low-dimensional space to reveal structure, features, and latent patterns. Through inversion mapping, it can reconstruct patterns or vacancies identified in the low-dimensional space back into the high-dimensional space to interpret their original meanings. Nevertheless, even GTM-based patent map approaches remain limited as patent vacancies can only be described at the keyword level, leaving their definitions ambiguous. Therefore, this study aims to utilize an embedding inversion model to translate technological vacancies identified in patent map into human-readable text, thereby enabling the discovery of new technology opportunities. This is the lative work stage. EOD aims to identify potential technology gaps by analyzing patent data with one representative approach being the construction of a technology function matrix. However, TFM relies heavily on domain expertise and manual classification, which limit its scalability in terms of time and labor. To address these limitations, visualization-based TOD approaches using patent map have been proposed. Patent map visualized patent data in a two-dimensional space, enabling the identification of patent regions. With the introduction of generative topographic mapping (GTM), the precision of patent map generation and vacancy detection has improved. Nevertheless, GTM-based approaches still describe technological vacancies only as a set of keywords, lacking the ability to express them in a human-readable relative form. Understanding the spatial distribution and concentration of patent within a technological domain is essential for identifying both active research areas and potential opportunities. To achieve this, density estimation techniques are employed to transform discrete patent location into continuous subspace, representing the overall intensity of patent activity. Particular kernel density estimation is a non-parametric method that applies kernel functions to estimate local densities, making it useful for identifying technological hotspots. This study employs KDE to measure patent density and detect potential vacancy regions. Embedding inversion is a technique that reconstructs high-dimensional embeddings back into their original data forms, and its applications have recently expanded into the text domain. Among such approaches, the back-to-text model proposed in previous research has demonstrated that it can accurately reconstruct original text using only embedding vectors without any additional information. Unlike other generative models such as GPT-4 or T5, back-to-text is specifically designed to take embedding vectors as direct inputs and restore them into texture representations. Therefore, this study employed back-to-text to convert technological vacancies identified in patent map into human-readable text descriptions. This is the proposed approach stage. Shin described the proposed approaches which generated a patent map based on patent data, identifies patent vacancies within the map, and convert those vacancies into human understandable text. Figure 2 presents the overall framework of the proposed approach, which consists of 5 steps as follows. Explain in more detail. In the first step, patent abstracts are converted into 1536 dimensional embedding uses a text embedding model based on the vector space of a selected plantain model. In this study, OpenAI's text embedding ADA002 model, which is known for its strong performance in capturing semantic information, is employed. This choice offers the advantage of being directly compatible with back-to-text as the model was trained using the same embeddings, allowing it to be utilized without any modification or retraining. The second step involves autoencoder training, where the high-dimensional embeddings of the transformed patent abstract are used to train the model. An autoencoder is a neural network composed of an encoder and a decoder designed to compress input data into a low-dimensional space and then reconstruct it, thereby learning the essential features of the input. Accordingly, in this study, the dimensionality of the latent space is set to 2, representing each patent as a two-dimensional vector, which is then utilized from constructing the patent map. In the third step, the patent map is generated through dimensionality reduction and density estimation. The autoencoder trained in the previous step compresses the high-dimensional embedding into two-dimensional representations, generating coordinates that indicate the relative position of patent abstracts. A grid-based patent map is then constructed, and the patent density of each cell is calculated to identify candidate vacancy regions. Subsequently, KDE is applied to estimate the hotspot and cold spot areas of technological activity, enabling simultaneous identification of both activity and on-spot regions. The fourth step involves vacancy identification, which is performed at the cell level within the patent map as shown in Figure 3. Cells without data point are defined as vacancies. The final involves reconstructing the identified patent vacancies into human understandable texture forms. First, the two-dimensional vacancy coordinates are restored to the original 1536 dimensional embedding space using the decoder of the trained autoencoder. The reconstructed embedding vectors are then used as for vector-text, which converts them into human-readable textual description. This stage operates as a fully automated pipeline once the vacancy coordinates are identified, recalling no human
intervention during the text generation process.
This is the case study stage.
To validate the effectiveness of the purpose approach, this study conducts a case study using LiDAR-related patent. In the first step, LiDAR patent data were collected from the US video database. A total of 70,616 LiDAR patents were obtained, among which 12,239 patents from 2014-2021 were used for training and 5,377 patents from 2022-2023 were used for validation. Our patent abstracts were embedded into vector using the text embedding ADA002 model. In the second step, the octoencoder was trained using the patent embeddings generated in the previous step. During training, the mean squared error was used as the loss function to minimize the difference between the input and reconstructed output, while the ADMW optimization algorithm was employed to find the optimal parameters. Third step, a patent map for LiDAR technology was created using 12,239 patent records from 2014 to 2021. The high-dimensional embeddings were reduced to two-dimensionals through the encoder of the training autoencoder, and kernel density estimation was then applied to generate the final painted map. The resulting painted map was divided into zones from Zone A to Zone E according to density levels, and regions with density below 50% were included from the analysis. The fourth step, patent vacancies were identified in zones A, B, and C, which inhibited relatively high density. A total of 137 vacancies were detected across the three zones, and each vacancy was marked with the symbol X. The visualization result confirmed a reverse-inverse relationship between data density and the number of vacancies. Final step, the identified LiDAR patent vacancies were reconstructed into 1,536 dimensional high-dimensional embeddings using the decoder of the autoencoder trained in section 4.2. Then back-to-text was applied to restore these vectors into natural language text in the form of patent abstracts. Have one present the reconstruction result for three vacancies specified in Figure 5. Specifically, V1 describes vehicle sensor-based data processing. V2 pertain to cloud-based distance measurement device, and V3 explains optical parameter processing technology for LiDAR sensors. An additional validation purpose was conducted to evaluate whether the identified vacancies could actually lead to future technological opportunities. The verification focused on two criteria for this purpose. 5,377 patents registered between 2022 and 2023 were overlaid onto the patent map constructed from 2014-2021 data for comparison. As a result, 7 out of 8 vacancies in Zone A, 17 out of 42 in Zone B, and 38 out of 87 in Zone C were found to be filled by actual patent. Subsequently, the technological similarity between the reconstructed vacancy abstract and the actual patent abstract was compared both qualitatively and quantitatively. Three LiDAR technology experts evaluated the generated text and highly readable and coherent. In the quantitative analysis, cosine similarity based on the text embedding ADA002 model was approximately 0.9, while sentence spot based similarity ranged from 0.71 to 0.78, indicating a high degree of consistency. This result demonstrate that the proposed approach can successfully identify future technological opportunities from patent map and concretize them into human-readable text.
The discussion stage.
This section discusses the influence of hyperparameter selection, the interpretation of identified opportunity types, and the insight gained through temporal dynamic analysis of the proposed approach. First, vacancy identification using grid-based and KDE-based patent map is highly influenced by hyperparameter settings such as cell size and density threshold. Therefore, a sensitivity analysis is required to determine an appropriate cell size based on the purpose of technology opportunities analysis and the characteristic of the data. In the lighter case study, a cell size of 0.015 was adopted, considering data distribution and precision. In addition, KDE was introduced to reflect difference in technological and market significance, where high density region are interpreted as having fewer vacancies and greater technological validity.
Accordingly, this study focused its analysis on high-density lesions corresponding to the top 10% of patent density. As shown in Table 3, the number of vacancies in Zone A decreased from 69 at the cell size of 0.01 to 0 at 0.02, where the low-density lesion still contained numerous vacancies regardless of cell size. In addition, density-based zoning provides not just a matter of precision adjustment, but an important criterion for distinguishing type of technology opportunities. Vacancies in high-density region of the patent map represent incremental opportunities adjacent to existing technological frontiers, characterized by low risk and higher short-term visibility. Conversely, vacancies in low-density regions correspond to radical opportunities that remain underexplored, carrying higher uncertainty but also greater potential for breakthrough innovation. V4 and V5 in Jones D and E illustrate radical opportunities describing new beam physics and system correlations. However, vacancy abstracts in low-density regions tended to exhibit lower technical specificity due to data scarcity, indicating the need for complementary export evaluations. Beyond single-point vacancy analysis, understanding the temporal dynamic of the technological environment is essential for capturing the emergence, maturation, and decline of technological opportunities. Figure 7 visualizes the change in Lidl patent vacancies from 2050 to 2023, showing that while numerous vacancies existed in the early years, they were gradually built over time, reflecting an overall trend of technological maturation. During this period, the total number of vacancies decreased from 4,492 to 939, with the high-density regions sharply declining from 73 to 1, indicating intensive R&D activity and technological saturation. Lower panel of Figure 7 illustrates the logical progression through which vacancy abstract evolves into actual subsequent patent via citation-based trajectories. For example, the connection between the optical distance measure device and method and system for lidar transmission demonstrate how a vacancy is gradually built within the technological development process. This provides important insight for determining strategic intervention point and guiding investment decision. The conclusion stage.
This study proposed a novel approach that transformed patent vacancies into human-readable text, a capability previously unattainable with traditional methods. The proposed framework is not restricted to the specific technological domain and demonstrates universal applicability across various fields by leveraging the semantic information embedded in text. Furthermore, it presents potential as a vertical decision support tool for corporate technology strategy development, R&D roadmap planning, and competitive technology analysis. However, the proposed approach has several limitations. The employed back-to-text model tends to generate short text than typical patent abstract, suggesting that future research should focus on improving the model architecture or fine-tuning it with patent-specific dataset to achieve more refined reconstruction quality. In addition, since this study primarily focused on vacancy identification and text generation, future validation is required to assess the long-term value and market potential of the identified vacancies. Lastly, longitudinal studies are needed to verify the applicability and translation quality of the approach across different languages and patent databases, as well as to evaluate its predictive capability and practical effectiveness. This concludes my review. Thank you.